Hey everyone, and welcome to This Explainer. Today, we're sketching out the hidden and honestly kind of terrifying dangers of process pauses and system uncertainty in distributed architectures. You know, if you've ever built a distributed system, you already know the network is a complete mess. But today, we're actually looking inward at the nodes themselves. We're going to explore why a perfectly healthy running process can just unexpectedly freeze, why the rest of your system might mistakenly declare it totally dead, and how these invisible pauses can create massive uncertainty and even corrupt your data if you aren't prepared.
All right, let's quickly hit our roadmap for today. We're covering the illusion of continuous time, why systems freeze in the first place, the zombie leader problem, the anatomy of a data disaster, and finally, how fencing tokens save the day.
So, kicking things off with part 1. The illusion of continuous time. To really get this, we need to completely shatter a common beginner assumption about how code actually executes on a server.
Seriously, I want you to ask yourself right now, what would your backend do if a running process just vanished for 15 seconds and then woke up completely oblivious to the fact that it was ever gone? Imagine a thread checks the time, verifies it has a valid lock on a file, and then, boom, right before it writes to the database, it gets suspended. For 15 whole seconds, the rest of your system just keeps on moving. Leases expire, new leaders get elected, and then your thread wakes up, totally unaware of that huge time gap, and just goes ahead and executes that write.
And that, right there, is what we call a process pause. The node isn't actually dead. It hasn't crashed at all. But to the rest of your distributed system, it certainly looks like it has. And the really terrifying part is that the node itself has absolutely no idea it was paused until it explicitly checks its clock again.
Okay, moving on to part 2. Why do systems freeze? So what actually causes these invisible freezes in the messy reality of the physical world?
You might be sitting there thinking, hey, my code is super optimized, this won't happen to me. Well, these pauses often happen entirely outside of your application logic. Here are the silent culprits. First off, runtimes like the Java Virtual Machine have garbage collectors that occasionally just need to stop all running threads. These stop-the-world pauses, they've been known to last for literally several minutes. Then, you've got virtual machine live migrations, where a VM is basically suspended just to be moved to another host. We also see OS thread preemption, where the hypervisor forcibly switches to a different VM, causing what's known as steal time. Oh, and don't forget synchronous disk I/O stalls, or the operating system paging and swapping memory to disk. Basically, underneath your code, your system is constantly stopping the world.
This all comes down to a core trade-off we make in modern engineering. Sure, you have extremely expensive hard real-time systems, like the ones controlling aircraft or rockets, that avoid this entirely with strict timing guarantees and dedicated hardware, but standard cloud servers, they operate very differently. They trade those strict timing guarantees for high resource utilization and cost efficiency. You know, multi-tenancy and dynamic resource partitioning are fantastic for your cloud bill, but it means we just have to suffer these unpredictable pauses natively.
Which brings us to part 3, the zombie leader problem. Let's look at how these pauses create absolute chaos, specifically when we're dealing with leader nodes in a database or a job scheduler. Let's actually trace this out on a timeline. At second 1, a node happily acquires a lock, firmly believing it's the leader. All good, right? But at second 3, a massive stop-the-world garbage collection pause hits. The node is completely frozen. By second 12, the other nodes in the cluster hit their timeouts. They decide, yep, this leader is dead, so they go ahead and elect a new one. But then, at second 16, the original node wakes up. And because it hasn't checked the clock yet, it still thinks it's the boss.
We call this a zombie node. It's essentially a process that resurrects from the dead and blindly continues executing instructions that are now dangerously out of date. It's just happily acting under the totally false belief that it is still the chosen leader.
Now, on a single machine, we'd just use thread-safe mutexes and shared memory to prevent this kind of conflict. But you have to remember that standard single-machine logic simply does not translate to distributed systems over unreliable networks. There is no shared memory. There's no magical global variable you can check to see if you're truly still the leader. You only have messages sent over a network, and those come with wildly variable delays.
And that leads us perfectly into part 4, anatomy of a data disaster. Because we don't have shared memory, and because zombie nodes are a real thing, we are perfectly set up for a catastrophe.
Let's trace exactly how this breaks your application. This actually mirrors a real bug that systems like HBase used to have back in the day. Look at client 1 up there. It asks the lock service for a lease, gets an OK,
And boom, client 1 is now the leader. But immediately after that, it hits that gray box. That's our Stop the World GC pause.
So, what happens next? Well, while client 1 is stuck in that gray box, its lease expires. The lock service naturally assumes client 1 has crashed, so it grants a shiny new lease to client 2. Client 2 then writes its data safely to storage. But wait, zombie client 1 wakes up. Still believing it holds that valid lock from before the pause, it fires off its own write to the storage, and the result? A massive clash. The storage accepts both writes, and your file is permanently corrupted. Nightmare scenario, right?
So how do we stop this? That's part 5. Fencing tokens save the day. We clearly can't trust our own node's perception of time, and we can't perfectly distinguish between a crash node and a pause node.
The fix is defensive coordination, specifically something called fencing tokens. A fencing token is a brilliantly simple concept. It's really just an ever-increasing sequence number that gets granted every single time the lock service hands out a lease. The magic here is that the storage server itself uses this number to actively validate every single write request. Let's sketch this out and notice the difference from our previous disaster. This time around, when client 1 gets the lease, it also gets token number 33. Then it hits that nasty GC pause and the lease expires. Client 2 comes along, asks for a lease, and the lock service hands over the lock along with token 34. Client 2 sends its write to the storage server, explicitly attaching that token 34 to the payload.
And here is the absolute crucial point. The storage server actively remembers the highest token it has processed. So it successfully processes client 2's write with token 34. Now, when our zombie client 1 finally wakes up and tries to send its much-delayed write with token 33, the storage server basically acts like a club bouncer. It looks at the request, sees that 33 is less than 34, and just flat-out rejects the zombie's outdated request. Boom. Data corruption prevented.
The big takeaway here is that in distributed systems, you literally must design for uncertainty natively. You can never, ever truly know if a node is dead or if it's just taking a really long nap because of a page fault or a garbage collection cycle. You cannot rely on a single node's judgment or its local clock to keep things safe. You've got to implement mechanisms like fencing tokens, careful timeouts, and idempotency across your entire architecture.
So I'm going to leave you with this. Go check your system's architecture today. Really think about your lock services, your leader elections, and your storage endpoints. Are your distributed locks actually secure with defensive coordination, or are you just operating on the illusion of continuous time, waiting for a zombie node to wake up and completely corrupt your data? Thanks so much for joining me on this explainer. I really hope this session gave you some powerful new tools for your own distributed architectures. See you next time.